Section 15.9, Change of variables in multiple integrals. The change of variables is a very important and useful tool, particularly for vector calculus. In chapter 16, we'll use it again and again. So you have to understand it quite thoroughly. You have done changes of variables several times in the past. For example, in Calculus 2, you learned integration with the u substitution. For an expression of x, you introduce the u as a function of x. Then for this type of integral, you can get it quite easily. You did this change of variables. Another way of the change of variables is here. Now we consider x as a function of u rather than u as a function of x. Then this dx will be, the differential will be this form, and correspondingly the lower bound, upper bound must be adjusted as the limit of u. And let's see this example, then you can understand these two different ways of getting the change of variables. Okay, evaluate from 0 to 2 x e to the x squared dx. And earlier you did this. We introduced u as a function of x, u equal x squared. Then du as 2x dx. So x dx here, x and dx is the same as half du. When x is 0, u is 0. When x is 2, u is 4. So that the given integral here is the same as, now, integral from 0 to 4. And this portion is e to the u. Okay, that portion is e to the u. And x dx is the same as half du. So half can come out. And integral from 0 to 4, e to the u du. Antiderivative of this exponential function is the same as the original function. So that we recheck this one, and after evaluation, we can get this final answer. Now, rather than introducing u as a function of x, let's consider x as a function of u. Then from here, we can easily see that x is square root of u. Then, now u derivative, dx over du, is 1 over 2 square root of u. So the given integral is changed in this way. Of course, when x is 0, then u must be 0. When x is 2, then u must be 4. So that for u, the lower and upper bounds are given in this way. X is square root of u. And x squared is u. And dx is same as 1 over 2 square root of u and du. And half came out, this coefficient, and square root of u, this square root of u, cancelled, so that we reach at this one. But this one is exactly the same as that one. Okay, so that we can get the same answer. Here the main difference is here. In x domain, okay, this is in x domain, you have integral over a to b. Earlier, you defined u as a function of x. Now we'll try to define, and we try to introduce u such that x is function of u. U is here, and try to express x as a function of u. So in a sense, u is a kind of a pre-domain of this domain. But either way, for the same problem, you can get the same answer. Okay? Yeah. See this example. The change of variable is also useful in multiple integrals, as in double integrals in polar coordinates. For polar region R, we have used the conversion formula, and xy are expressed in this way. That means that for given xy, here from r and theta is defined. So that is basically the transformation. So r theta is the variables in the pre-domain, and xy is the domain we are dealing with. So that is exactly one example of using pre-domain variables. Okay, so integral over r in xy domain can be written from the pre-domain q and f as a function of r theta, and r dr d theta. This r is the scaling factor. So that is exactly an example of using a pre-domain. Okay. Now we'll study it quite systematically so that you can apply this technique for very important problems. A change of variables is a transformation t from q to r, from the uv plane to the xy plane. In this way, so x is a function of uv, and y is also another function of uv. So we may write down in this way, all uv is this vector, and g and h, and that is a change of variable. But here, the transformation must be differentiable. C1, this notation means that derivative is also continuous. And once it is continuous, then we are using the notation C0. And first derivative is continuous, then C1. And for example, the second derivatives are continuous, then we use C2, and so on. And also, the transformation must be one-to-one. The reason is that, okay, here, in this region, when you try to get integral, then you have to access this domain once and only once. So by using one-to-one transformation, and this access once and only once can be now done in this region with accessing the points once and only once to guarantee it. The function must be one-to-one. And also, the integral is based on the Riemann sum. In fact, integral is the limit of the Riemann sums, so that here the areal components must be considered. That is along with your scaling factor. To find correct scaling factor, the transformation must be differentiable and continuous. Okay. Okay, in this example, we consider a transformation. A transformation is defined by here, so that is x and that's y. Okay, find the image of the unit square q. Okay, that is pre-domain, and we try to find the domain. The unit square is now in UV domain. Okay, there is U direction, there is a V direction. We have unit square here. There's 1, this is the origin, and 1, like that. And for this one, we want to find now image of this one through the transformation. Of course, this is the x direction, that is y direction. Okay, this is, each one is linear, so that line segment will be transformed into a line segment in xy domain. So we may focus on the corners, then connecting, by connecting the corners, we can get the image. Okay, here, this is 0 and 0. That is now x is 1, y is 0. This is 1 and 1. This is x is, okay, x is 0 and y is 1, so that we can write in this way. For these 4 points, okay, the operation, the transformation is given in this way. And here u and v are 0, then, and the first component will go to 0, and second component again 0. Now u is 1, v is 0, then u is 1, then it will go to 2 and 1, right? Okay, u is 0, v is, okay, u is 1, v is 0, u is 1, 0, okay? Now 1, 1, from 1, 1, u is 1, v is 1, then there is 1, first component 1, and second component will be 2. How about for the last point, 0, 1. So it's 0, 1. Then it is first component minus 1, 0, 1. That is 1, right? Okay. In xy domain, for that one, it's 0, 0. And now 1, 2, 3, and 1. So that second point will be this one. And third one is 1 and 2. Okay, we have here. And last one is minus 1, and y component is 1. So here. So if we connect them in the order, then we can get the image. That's the answer. Okay. Now we'll try to see the effect when we try to use this change of variable. And of course, double integral over R will be done here, double integral over Q. Either side, okay, this is F, then we have here F and some scaling factor. So some scaling factor must be given based on the change of domain. So it's a kind of an aerial component. We have to consider that one, because the integrals are defined as the limit of Riemann sum. The f is the same, but here this one must be given so that we can get the same answer. Okay. Now, assume we have transformation from UV domain to XY domain, and we have a general domain, in fact, in this case is beta domain, and this side general domain. Now, for this one, for example, rectangle, once we partition into X direction, Y direction, then for small portion, small sub-rectangle, assume we have image. So that is R, so that's Q, and that's R, is the general shape. Okay. So we focus on only small sub-region, one sub-region. Then we try to see how these areal components are related. Okay. Now, obtaining the area of that exactly is not easy. So that here we try to approximate this region by using the parallelogram. We try to get the image of this one, so that for R function here, R sub U, so that directional vector times delta U, the length is delta U, that is exactly this vector, and R sub V is the image of that directional one, V directional derivative, and delta V. That is exactly the image of this vertical line segment. Now, these two vectors will make a parallelogram, and we'll try to get the area of the parallelogram and use this area to approximate the area of original region. That's the idea. And once you do this one, then once you try to partition more and more in each direction, then here the approximation is more accurate, so that you can get the right answer. Okay. So we try to get area of the parallelogram. That is here the length of the two vectors is unknown, and the parallelogram made by two vectors can be obtained in this way. The length of the cross product of two vectors, delta U, delta V are constant, so that we can put it out, and we recheck this one. Now, let's try to get R sub U cross R sub V. That is the determinant of this metric, ijk. Now, we consider this R sub U and R sub V and a vector embedded in 3D, so the third component is 0. So that is R sub U embedded in 3D. This is R sub V embedded in 3D. Then if you do computation, then you can reach at that one. So determinant is now this product minus that one. And so here, that is same as now x sub U, y sub V minus y sub U and x sub V and K. K is unit vector in the vertical direction. So we try to measure the length of that one, so that eventually absolute value of that one will be used there. Here we define Jacobian of the transformation in this way. That is the determinant of this one, xu, xv, and y, u and v derivative. In notation, we are using this one for xy. We are making here uv derivative, and take the determinant. This one itself is called the Jacobian metric and determinant. And now that is a kind of a scaling factor, but it's area component, so that we have to use the length of this one. So we'll use absolute value from this one. Okay, so we summarize here. Now the transformation is differentiable. Then now delta A in xy domain is approximated by here delta U delta V times and this absolute value of the Jacobian. So we can get it into this theorem. T is C1 transformation, and whose Jacobian is non-zero, and here T maps a region Q in the UV plane onto a region R in the XY plane. And also we assume here T is 1-to-1, then we have this one, double integral over R is the same as double integral over Q, and this is F as a function of UV, and this is a scaling factor, the absolute value of the determinant of Jacobian metric. Okay, that's the theorem. Okay, now we'll go back to the transformation for the polar coordinates. Okay, now here, now if we consider this transformation, x is function of r theta, and practically r cosine theta. Y is a function of r theta, that is r sine theta. Then, now for this one, this is x r derivative and x r theta derivative, and for that one, now y r derivative and y theta derivative. So that is the Jacobian metric and determinant. Then here, this product is r cosine squared theta, and minus, again, we have another minus, so that plus r sine squared theta. So we reach at r. That is exactly the scaling factor. And using that, here, integral, double integral over r in polar region can be transformed in this way. Of course, here, now in polar region, we assume that now r is between a and b, and angle is from alpha to beta, so that it is a polar rectangle. So we can get this integral along with the scaling factor. Right? We did this one already when we learned the polar coordinates. Okay, that's part one for the key idea, and we'll continue in the second part, and we'll try to solve some practical problems. Thank you.